Hi, I'm Jim Heffron. These are my lessons in Calculus 1. And today we're doing the derivative of logarithms, which of course are the inverse of the exponential function, and inverse trigonometric functions. And at the end, we'll talk about derivative of inverse functions in general. Okay, will be fun. Let's get started. So let's see. We're thinking about here the derivatives of logarithmic functions first. So I want to remember a couple basic facts about logarithms. This is a good place to put the basic facts. So you recall that the expression log base b of y, the expression log base b of y equals x, is equivalent to the expression b to the x equals y. That is to say that if I write down log base b of y, I'm asking the question b to the what equals y. So the x here is the x here. If I write down b log base b of y, I'm asking the question b to the what equals y. When the base is e, which is approximately 2.718, you write ln instead of log base e. ln of y equals x if and only if e to the x equals y. Okay, so here's a picture. This happens to be a picture of the ln. You notice a couple things about it here in the bullet point. First of all, the domain of ln is positive reals. We're not doing complex numbers here, so the domain of ln is positive reals. If you give me, for example, you ask me what is the ln of minus 1, I'm going to say minus 1 is not in its domain. The ln of 1 is 0. There we go. ln of 1 is 0. The limit as x approaches 0 from above of the ln is minus infinity. That's another way of saying that. There you go. You have an asymptote headed toward minus infinity as x heads toward 0 from above. And then the last one, as x heads to infinity, the ln also heads to infinity, although it does so very slowly. And so you might say to yourself, I don't know, maybe it levels out. It never quite does level out. It goes to infinity, although it grows very slowly. Okay, so all of these facts here should be, all the ones on the prior slide and all the facts here should be memorized. First of all, the definition of ln immediately gives that ln and e to the x cancel each other. It holds for any base logarithm, but we're most of the time going to work in base e. And ln and e cancel each other in the other direction also. This formula here to convert between bases means that if you want to work in a base other than e, it's convenient sometimes, for example, to work in base 2 when you're a computer person. If you want to work in a base other than base e, you can always use the numbers from base e and do the conversion. So what this tells you is that the log base b of x is 1 over the natural log of b times the natural log of x. That is to say that all logarithmic functions are proportional, and the constant of proportionality is right here. The other fact about logarithms that very important, the logarithm of a product is the sum of the logarithms. Logarithms, in particular a natural logarithm, turns multiplication into addition. Okay, and I gave an argument for that for those people unfamiliar with the argument, but I'm not going to go through it. Because of that fact, if you had, for example, that you were looking at ln of x times x, you would have ln of x plus ln of x. So that is to say ln of x squared is twice ln of x. And in fact, that works for any n in general. So the number in the power moves out front. Likewise, similarly, reciprocals become negatives and quotients become differences. If logarithm turns multiplication into addition, you're not surprised to find that logarithm turns division into subtraction. And everything on that screen, everything on that page, a person should know, should memorize. And then the derivative of derivative of logarithm base b. Naturally, we're interested. This is calculus class, so we're interested in the rate of change of that function. And here's the derivative of the logarithmic function in general. And here's the derivative that we are going to use an awful lot in this class, or very, very lot in this class. Derivative of natural log is 1 over x. The proof is not really very tough, but it needs implicit differentiation, which is why it comes after the implicit differentiation section. So you have b to the y of x equals x, and then you take the derivative with respect to x on both sides. So you take d dx on both sides, d dx on both sides. You of course get 1 over here, and here's the chain rule. And then you just solve for dy dx, and you end up with the expression that we promised. Okay, so you need implicit differentiation, but once you have it, it isn't very hard at all to come up with the formula. You know how I like to work. I like to, after we see a fact, like the fact on the prior slide, I like to practice it. So I think the right thing to do here is to pause this video and try the problem and see how you do. If you get stuck, then of course you'll see the answer, and you'll figure out what it is you were having trouble with. Okay, so I'm pausing for a second. Okay, great. I'm trying to find the derivative of the natural log of some function of x, so it calls for the chain rule. And here it is. The chain rule natural log gives 1 over, so 1 over the argument, not 1 over x, 1 over the input, and the input here was x cubed plus 3x plus 4. So 1 over x cubed plus 3x plus 4, and then finally the derivative of what's inside. So a person could write under bars here, as I so often do. Next up, the product of x times ln of x. And it calls for the product rule. You write down the first thing, and then you take the derivative of the second, and you write down the second and take the derivative of the first. And it so happens that the x and the 1 over x cancel each other, and you just get 1. Third. Okay, quotient rule, I just simply ground it out. I didn't try to do anything fancy here. So you recognize that you have to take the denominator squared, and then you've got to write the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. So, of course, the derivative of the numerator calls for a chain rule problem. Ln of x squared is a ln of a function of x, so I applied the chain rule here. So I could have put in under bars, and then a little bit of algebra, and it turns out that you can cancel one of the x's and end up with x cubed on the bottom. Okay, so this fits in to the context, chain rule, product rule, all that kind of stuff of the things we've seen before. It just adds a new tool to that, namely the derivative of the logarithmic function. Okay, next up is a derivative of another inverse function, derivative of inverse trig functions. I'm going to do the derivative of arcsine. You could do all the others. I'm just simply, have to do some one, so I'm going to do the derivative of the arcsine function. So I'm reminding a person what arcsine means, that the arcsine of x equals y simply means that the sine of y is x. So the arcsine tells you the angle when you know its sine. Okay, so if you know the sine, then you find out the angle. So that means that you could take that angle and plug it into the sine, and you would get out the sine. Okay, and here's the picture that the angle, you're given the opposite over hypotenuse, and the angle is the arcsine of the opposite over hypotenuse. Okay, and of course the same holds for arc cosine, arc tangent. I could have written arc secant, arc cosecant. I didn't. I just wrote the three sort of biggies. The derivative of the arcsine function, we're going to go through it two ways. One way is I'm going to take the implicit differentiation. So if I want to take the derivative of the arcsine function, then then I can put it in this form: the derivative of the sine of y equals x. I'm going to take the implicit differentiation, so I have sine of y of x equals x. Take the derivative of both sides, so the derivative of x is the 1. Derivative of a sine of y of x, well, you take the derivative of the cosine. Take the derivative of the sine, and there it is, the cosine, and there's the derivative of the function that's inside, the y of x. So chain rule, have the underbars. Solve for dy dx, and you're looking at dy dx equals 1 over cosine of y. Now, there's nothing wrong with that formula except that I want the derivative here. I want the derivative of the arc sine of x, and this gave me an expression that's in terms of y, so I got to convert it back to x's. Convert it back to x's, I'll use, of course, the familiar familiar expression that the cosine squared plus sine squared equals 1, to rewrite the cosine as 1 minus sine squared of y square root. And of course the sine is all the way up here. Sine of y, there we go, is x. Okay? So I just replace the 1 over cosine with 1 over the 1 over this, the 1 over the 1 minus x squared square rooted. Now, it might be surprising to a person that it doesn't have some kind of trigonometric expression there. You might have been thinking that the derivative of arc sine is going to be something like the arc cosine, or maybe negative arc cosine or something. But you happen to get, from trigonometric expressions, you happen to get that. The other ones are similar. So a person should memorize, it seems to me, the derivative of should memorize the derivative of, if I can get my pen to work here, there we go, derivative of these three. Okay, in particular in calculus 2, those are the three that you're going to need. Okay, but you also notice that it doesn't say anything like the derivative of the arctangent is the arc cosecant or something. It's maybe a little surprising. The exact form of the formula is maybe a little surprising. As usual, I like to do a practice, so I'm going to do practice, same thing where I ask you to pause the video and try it yourself, and then come back and see if you got the right answer. So the derivative of the arctangent of square root of x. All right, so let's see. Arctangent, you have to take the derivative of the arctangent part, and then you have to put the square root of x into that. Derivative of the arctangent part is over here, of course, 1 plus, 1 over 1 plus the input squared, and the input in this case, of course, we know is not x, but instead is square root of x. So that's the derivative of the outer function, and then the derivative of the inner function. Of course, the derivative of square root is familiar. We've done it so many times. 1/2 1 over square root of x, and then I just combine them. I mean, you take the square root and you square it, and etc., and you get this for an expression. Okay, next, please. So product rule, this is a product of two functions of x. It all fits into the same rubric we've been developing all semester. So I wrote down the first, took the derivative of the second, wrote down the second, and took the derivative of the first. I did some algebra here. Let's see. I guess there's a 2x, and I wrote it in front there, and I combined this into the numerator, but really nothing exciting, and I just got that expression. That's all there is to it. So all this quotient rule, product rule, all that stuff still fits. Of course, it still fits, but anyway, it does still fit. I'm just going to very briefly go through geometric proof of the derivative of the arc sine. The form of the answer for the derivative of arc sine is surprising, I think. So it's sometimes a help for a person to feel like they got where it came from. So I'm going to figure out what is the derivative of arc sine. So I wrote down the arc sine relationship here. And theta equals arc sine of y, and so here's the theta and here's the y. And now I'm going to take the derivative, so I'm interested in what happens when you take the arc sine of sort of y plus delta y minus arc sine of y over delta y. So I needed to have the arc sine of y plus delta y, and I fit that into the picture. And what you're expecting to see happen is it would drop some perpendiculars, find an appropriate geometric relationship, that kind of thing. And that's exactly what's going to happen. So here we go. This is the picture from the previous page, except some things have changed from red to black. And I dropped a perpendicular here, I dropped a perpendicular here, and I also put in a horizontal there. I'm recognizing the relationships. This is, of course, a unit circle. This is a unit circle. So we have x equals cosine theta and y equals sine theta. And just I'm going to need it in a couple minutes, so note that x is the square root of 1 minus y squared. I'm going to relate the change in theta to the change in y by using the small triangle in the upper right. Here's the small triangle right here in the upper right. Okay, so I did some stuff that you might think, well, there's going to be some perpendicular dropping. Absolutely right. So here we are looking at that small triangle in red. In that small triangle, we have an angle in the upper left, this angle right here in the upper left, and it's approximately theta. So just to go through the reasoning, here is the angle theta. This is alternate interior angle right here. That one's certainly theta. And that one and that angle and this angle here are very close to being complementary. This delta theta is small, so that's very close to being a 90-degree angle there. Can I make the little 90-degree angle sign? That's very close to being a 90-degree angle. So, oops, lost my way. Here we go. This is very close to being a 90-degree angle. 90-degree angle. So this angle down here is very close to being the complement of this angle here. And of course, the complement of this angle here is this angle here. So I find myself with what's in red as being very close to theta. And the approximation improves as delta theta goes to 0 because that becomes more and more like a 90-degree angle. The small triangle's hypotenuse is approximately delta theta. There we go. Erase, 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 erase. The small triangle's hypotenuse right here, right here, is approximately delta theta because we're working in radians, where the arc length equals the angle measure, and that hypotenuse is very close to the length of that arc. Approximation gets better as delta theta goes to 0, which it does, of course, when you take the derivative. The small triangle's leg on the left, this leg right here, the small triangle's leg on the left is a delta y. Delta y, delta y, delta y, delta y. Delta y is the hypotenuse times cosine theta, and because this angle is approximately cosine theta, and so that's approximately delta theta by cosine theta, delta theta by the square root of 1 minus y squared. Do you remember from the prior slide the square root of 1 minus y squared? Here we go. The square root of 1 minus y squared is cosine theta. So we're looking at the delta theta by the square root of 1 minus y squared. And in the limit, we have equality. That is to say, when, for example, delta theta gets to 0, we have equality. So you solve this expression to get that delta theta. So you move the delta theta over. You solve this expression to get that delta y over delta theta is 1 over the square root of 1 minus y squared. Okay, so the same, really pretty much the same argument, except that it's more of the kind of argument that a person is familiar with from kind of high school geometry class. Although the approximation improves as delta theta goes to 0, is kind of a less familiar argument. Okay, so we've done the inverse of exponential functions, namely logarithmic functions. We've done the inverse of trigonometric functions, arc, sine in particular we focused on. And now we're ready to talk about general inverse functions, what happens in the general case. So I want to talk about inverse functions for the moment. So you recall that two functions are inverse. If two functions are inverse, if when you compose them, you get the same input and output, same output as input in both cases. There we go. That wasn't bad. Same output as input over some appropriate domains. Examples of inverse functions are f of x equals e to the x and g of x equals ln of x. Likewise, f of x equals sine x and g of x equals arc sine x. Of course, you have to pay attention to the domain. You want to make sure that you're using what's called the principal angles. But anyway, over some appropriate domain. And f of x equals x squared, g of x equals square root of x. Those are all familiar cases where one function is the inverse of the other. And we denote the relationship as G equals F superscript minus 1. And it's sometimes a cause of confusion, but used not all that often. A person might think that means 1 over, but it's not all that much of a source of confusion. Here's the right picture to look at. These two functions are inverse. They actually happen to be the exponential function and the logarithmic function. So this is ln of x, and this one here is e to the x. Two functions are inverse when anytime you have the point a comma b, well, down here is the point b comma a. Then in other words, you have input output. Well, it's output input. And from that, you immediately see that that the geometric picture, the way they look, is that two functions are inverse if one is a reflection across the line y equals x. This is the line y equals x, the dashed line y equals x. If one is a reflection of the other across the line y equals x. So this is e to the x and ln of x. You see that relationship. This one is x cubed and cube root. You see that one there. And cosine and arc cosine. Cosine and arc cosine. You see that one there. Okay, all three cases you're looking at a reflection. One is a reflection of the other across the line y equals x. And here's the picture that tells you what the idea is. I took the natural logarithm and exponential picture for illustration just because you got to pick something. And this one, the two don't cross, so there's no muddying of that picture. Anyway, I'm looking at the I'm looking here at the rise over run, and here at the rise over run. And I think you see that the one is the reflection of the other. So if this is P and Q, if this one here is P and Q, then this one here is Q and P. Again, if this one here is P and Q, so what do I got? I got change in Y is P, and change in X is Q. Then this one here must be, just by virtue of being a reflection across the line Y equals X, this one here must be change in Y is Q, and change in X is P. So a function and its inverse have derivatives that are multiplicative reciprocals. You multiply the two of them together, you get a 1. Said another way, the one is 1 over the other. A second way to see the same thing is to think about the side-by-side axes picture of function composition. So we know that function composition for inverse functions exactly means that if you put the two functions together, you end up back where you started from. If you started from A, then you end up back at A. So you started from A, taken together, you end up back at A. And now remembering that the derivative is the local expansion rate of the function. If f, for example, doubles intervals in size, well then f inverse has to halve them in order to end up with the same interval that you started with. Again, if f is an interval doubler, so that the derivative of f is 2, then g must be an interval halver, so that the derivative of g is a half. So they're reciprocals of each other. It must be the case that the derivative of g is 1 over the derivative of f. Well, you've got to put in the appropriate letters here. The derivative of g starts at b, and the derivative of f starts at a, but nonetheless, you get that the two of them are reciprocals. So put down, I used x's here instead of a's and b's. Put down in terms of a formula, let f be differentiable and invertible, and the inverse is g. Then the two derivatives are multiplicative inverses, so that the derivative of the inverse is the inverse of the derivative of the function. But of course, it has to have the correct starting point. What on the prior page, the prior slide was b. All right, stated in a kind of a little bit harder to read form, but also correct form, that f inverse's derivative is 1 over f prime of f inverse of x. At just implicit differentiation, you take f of g of x equals x, and you differentiate implicitly, so you have the chain rule. You're looking at f prime, put in the correct input, times g prime. equals 1, and then just, solve. I mean, divide both sides by f prime of g of x. Okay, now that perfectly correct proof, of course, but it goes kind of fast, so I had a couple of previous slides that to give some intuition about what's happening here. I want to close by using this twice to make sure to check out that we get what we think we're going to get. So, I'm looking at the ln and thinking of it as the inverse of the exponential. Then the derivative should be f inverse prime of x. So you're looking at 1 over f prime of f inverse of x. So we know how to take the derivative of the exponential function, derivative of e to the, I'm reluctant to use x, derivative of e to the u is e to the u. And then don't forget to plug in the correct thing, got to plug in the correct thing, and there it is. We know that e and ln cancel each other, and when all the smoke clears, you just got 1 over x. Okay, one more, I don't like to do one example of anything if I can help it. So x cubed and the cube root. So you start off with the function x cubed, and we think, I think all of us think of the cube root as somehow the inverse of cubing. That's how I think was presented to me anyway when we started. Well, I don't know, what is that, 6th grade? So here we go. I'm going to take the derivative as a consequence of it being the inverse. So the derivative is just applying the formula. So it's 1 over f prime of f inverse. So we know how to take the derivative of the cube. It's, you write down the 3 and you take the 2 for an exponent, and what goes inside is not x but instead is f inverse, and there it is. That's the inverse. So x to the 1/3, 1 over 3 x to the 1/3 squared, and so I end up with a 1/3 x to the minus 2/3. 1/3 times 2 makes 2/3, and put it on the bottom of a fraction is minus 2/3. So, and that is indeed, of course, exactly what the derivative of cube root is. Exactly what the derivative of x to the 1/3 power is. Okay, all right, very good. So we've done the derivative of the inverse of exponential. We did the derivative of the inverse of sine, but more generally inverse of the 6 main trigonometric functions, and we did the inverse of functions in general, to take the derivative of the inverse of functions in general. So did a lot in a short period of time. Very good.